Okay, right now we need to focus on to analysis of the frequency response in terms of the what, the phase, and the magnitude, because we don't have any parameter besides this one. Okay, so how we can calculate the magnitude and the phase, which we call it the Bode plot in the technical literature. Okay, section 2, calculation of magnitude and phase. Okay, it's the Bode. First of all, we need to step-by-step analysis on this case. Okay, suppose that we have transfer function like this one. Hs is equals to the what? The 1 divided by s plus a. Okay, this function is written in the Laplace form, which means that the s must be equals to the what? The real part time plus times j times w. Jw represents the what? The frequency response, because if we have any imaginary part at the poles and then we have the oscillation. Okay, but in the real part, just like the unit or ramp or parabola or -5, -4, we have the time constant, but we don't have any oscillations. Okay, and so in order to analyze your system in terms of the frequency response, you need to assign the what? The j w must be equals to the what? The s. We need to extract the sigma or the real part of your systems. Okay, and so this must be written as the what? The h jw must be equals to what? The 1 divided by jw plus a. This only includes the what? The frequency regions. So these are the transfer function, but in the frequency domain. Okay, and so how can we calculate the magnitude and the phase in this case? Can be described by h jw must be equals to the what? The 1 jw a, and so using the complex analysis we can multiply these terms with the what? Jw, but with minus, and so we have in this multiplication complex conjugate form, this is the minus jw plus a, and so we have the a minus jw divided by omega square plus a square. Okay, and so we can split this form as like the what? The a w square a square plus j minus w divided by w square a square. Okay, and so in this case this is the real part, this is the imaginary part in here. Okay, we use that, utilize that, these terms in here. And so just see that if we have this kind of Euler identity or the formulation, and then how can we calculate the magnitude of these terms? And so square of the imaginary part plus square of the what? The real part, and then we need to plus these two concepts and the values, and then we need to take to what? To its square root form. And so the magnitude can be given as the h jw is equals to the what? The square root of the a divided by a square plus omega square plus and minus w divided by square omega square plus a square. Okay, and so in this case we have in a simplest form w square plus a square, the r, what? The magnitude of the r system. Okay, and so if we applied any frequency which is given in the what? The w, for example 10, 5, 6, and so this creates to what? The magnitude response on your Euler identity formula. Okay, because every sinus and cosinus creates the what? The Euler identity. And so if we have these characteristics like this one, and so we have also the time constant in here just like this one, and then we can create or obtain the magnitude values of the R system. Just see that this system always be positive at the magnitude, but we may have the what? The minus value in here, but always decreases its value when increases to what? To the R applied frequency. Okay, this is the magnitude. But we always gives in the form of the decibel form. This is the power form. For our case we have the what? The HJW dB must be equals to what? The 20 times log basis 10 can be given as the what? This one. This is important parameter for us because in the power form we can consider that, or we can define the cutoff frequency when the what? The total power TP, when the TP is divided by 2 or the half of it, and then this frequency is considered as the cutoff frequency. We cannot transmit the enough energy or the power to the other one, the other side. Okay, this is the what? The R decibel form or the energy form or the power form, but this is not the magnitude. This is the power of the magnitude in here. Okay, and so this power of the magnitude determines to the what? The cutoff frequency, which we need to stop, or which we need to change its cutoff in here, because the R system after the cutoff frequency does not run, cannot run. Okay, so in the second place we have the phase, and it's calculated by with what? Just remember this is the S-plane, and so we have the real part, and so this angle can be considered as the theta or phi value. In another terms, in the S-plane we have the imaginary part and the real part, and so this phi can be what? Can be calculated with the what? With the tangent formula. The tangent phi is equals to what? The imaginary divided by real, and so HJW is the what? Tangent minus 1 imaginary divided by real. Okay, and so in this case we have the what? The HJW can be assigned with the what? The tangent over minus 1 minus w square a square divided by with the what? With the a w square plus a square, right? This is the imaginary part, this is the real part, and so we can write that this is formula for the what? The w divided by a is the what? Is the phase representation of the R formulation, or this could be written as the minus arctan WA. Okay, these are the fuzz response for a given what? For a given different frequency values on this case. And so how can we prove that? We need to write a MATLAB code for this system. Okay, so this is the first example, and we need to comment all the terms in here, just like this one. This is the Bode diagram of the R system. Okay, X1. First of all, we need to define the A as equals to the 1. Okay, and also F, the log space, can be utilized in here. -2 to 2 and 400 values should be contained in here. This means that the from 0.01 Hertz to 100 Hertz are applied to this frequency. This is what the 10 over -2, 10 over 2, which equals to 100, and so we have the what? The 400 points in here. Okay, and so this important parameter is that the Bode plot should be utilized, or the W is in terms of the what? The angular frequency. Okay, because we are using the what? Euler identity, 2.pi.f. Okay, and so how we can calculate the magnitude of this term? What's the magnitude values of this term? The magnitude or the power form is given with what? The 20 times log basis 10 blah blah blah. Okay, and so 20 times log 10 and also 1 dot divided by sqrt the omega dot 2 plus a dot 2. Okay, this is the magnitude in the dB form. Okay, and also we need to calculate the fuzz minus a ton omega divided by a. Okay, but in the fuzz we need to give the degrees, not the radian one, and so times 180 divided by pi. Okay, fuzz in degree. So we need to build the figure in here just like this one, the subplot 2 1 1, and semi log x is a function of the what? F and magnitude. Okay, this is an important function for the semi log x because we can create the what? The basis with the what? The logarithmic domain. For example, we can assign the 0.01, 0.1 and 1 and 10 and 100, and we can create the changeable scale in the figure. Okay, and so the read on, and the title should be given with the magnitude plot. Okay, and the x label should be equals to the what? The frequency, Hertz, and y label is equals to the what? Is equals to the magnitude. Okay, but in the dB. Just remember that we assigned what? The semilog x as the f, which means that this is the Hertz. Its type is equals to what? The 1 divided by second. We can choose also omega in here, but in the real-time applications we need to utilize what? The f in here. This is a pre-described description for this time, because the pre-trained function given in the MATLAB, as we call it the Bode, draw this plot as the what? The omega versus magnitude. Okay, and also we need to give the what? To f and fuzz. Okay, and so is this fuzz given in the what? In the degrees. And so if I run this code, we will have this kind of information. This grids coming from the what? This grids coming from the semilog x. For example, 10 over 0, which means that this is equals to what? The 1. This is the 10. This is the 100. This is the 0.1 hertz. 0.01 hertz. Okay? And so, after all, in the second plot, we have the first degrees in here, just like this one. This is the representation of these terms. Okay? And so, how we can interpret this diagram based on this information? Just see that if the power is equals to the what is equals to the 0, which means that this the logarithmic term is equals to the 0. So, what does it tell us? If the logarithmic term is 0, and so we don't have any energy dissipation to transfer the input signal to the output one, the magnitude propose this form of terms. But just see that in order to analyze the R function in here, we can change the imag, the decibel form, with the what? With these terms. This R function, 1 divided by the magnitude, can be rewritten in here, just like this one. And so, if we calculate this one, and so this is the magnitude right now. The other one is the what? Is the decibel. And so if I rerun this code and then see that we have the magnitude in here. And so what does it mean to, for example, is the what is this location. If we apply the sinus signal to this system with the frequency rate of the what? The 0.1 hertz, our signal is diminished with the ratio of the what? The 0.84, which means that if we apply the 1 times sinus signal in here with the magnitude of the 1, our output gives us the what? The 0.84 degree in here. With beside of these terms, the R signal is to what? Possess the first degree in here, minus 32, which means that we shift the R signal to the left side at the output. This is the interpretation of these terms. For example, if we apply to what? To y and x in here, the x 30, which means that if we apply the sinus signal with the frequency of the 30 and then, which means that we reduce or diminish the whole signal at the rate of what? The 0.005, which means that we don't have any signal in here. Okay? For example, if we apply the 1 times sinus signal with the amplitude rate of the 1, and so at the 0.27 frequency, we have the half of the magnitude in here. For example, if we apply the 1 times sinus signal, and so we get at the 0.27 frequency, we get 0.5 amplitude. Okay? This is how we can analyze our system in terms of these times. Okay? So, this is the magnitude, but in the Bode plot, we utilize to what? The power dissipation in here, just like this one. Okay? For example, if I choose this section in here, just remember that what's the cutoff frequencies values of these terms. For example, this is the -3. This is the half of the whole of the power of these things in here. And so 0.15 value is not enough. Or the 0.15 value is the cutoff frequency at the what? At our signal, with the ratio of the what? Half of the power transmit to the another one, to another place. Okay? So, how we can change these parameters? For example, if I choose the A is equals to the 10, and so if we rerun this code and then At this case, see that the magnitude is equals to the what? The 120. And so the magnitude can be rewritten in here. For example, see, it's the 3. And so we can also copy of these things. 1, 2. Okay. And so magnitude Mach. It's the magnitude Mach. Okay. And so if I rerun this code, and then we can easily analyze our results. See that at the what, at the A is equals to the 10. And so at the beginning of this code, if we apply the 1 times sinus signal, and then we get to what? 0.1 amplitude, which means that 10 times reduce this signal at this system. Right? And so, but in this case, we have what? The minus 21 degree signal in here, in the decibel form. And so, we have dealt with also with this one. And the decibel one. These are two important properties of the what? The frequency response. Okay? Or if we set the 1 again in here, just like this one, see that if we have these terms just like this one, and so the R signal is at what? The 0.27, and so the half of the magnitude is transmitted to the what? To the another place in here. Okay, so the Bode plot can be utilized to what? In order to understand how your system behaves under the what? Under the input of the frequency domain. Because if you are selecting your system with the 10 ratio, and so your system is already diminish your results at the rate of what? 0.1 at this case, right? It's not useful for our case, but in some cases maybe we can utilize this property. Okay, this is the how we can measure the what? The input to output ratio based on what? The frequency characteristic. It's important. Even if you have the perfect system with controlled with the PID or the full state feedback or the nonlinear controllers, we must obey this rule, because everything is in the frequency domain, and so the input or the reference signal affects on the what? On your system. Okay, so in the second place, we need to talk about the what? The other terms. Also, we should use the Bode plot in here, just like this one with the G. Okay, and so the G can be defined with the what? The num 1. See that? Num 1, because the R system is the what? 1 divided by S plus A. Okay, and then can be equal to what? The 1 and A. These are the representation of these terms, and G, TF, num, and then, okay, these are the system. And so if we run this code, we have the same plot in the energy domain function, right? These times we have the characteristics, the system parameters. Okay, and so in the Bode plot we have the parameters just like the step function. This is our based on magnitude plot, but in the Bode diagram we can analyze the R system. For example, show magnitude and phase, specific frequency, poverty, and so the peak response is given at the what? At the frequency of the what? The 2 minus E11, right? And so this is so small, it can be considered as the 0. But Minimum stability margin can be seen at this time, but we cannot see that. The all stability margin can be seen at this one, okay? But we can not show this property because this system cannot be evaluated at these times, okay? But in the next examples we will consider of the whole of these things with by hand and the MATLAB code, okay? But this code is similar with the what with R codes, okay? But this is the basic calculation of the what the Bode diagram at this case. So next to but before begin with the what with the frequency domain, just remember that we have the section 3 just like this one, the Bode plots for GS is equals to what the S square plus 2 zeta omega n S plus omega n square, right? Because it's important, because it's a second order system approximation for the transient and steady state response, okay? And for the second order system we have these terms, and so the GS is equals to what the S square 2 zeta omega n S plus omega n square, right? And so the take the what the S is equals to JW, and then JW is equals to what the JW square plus 2 zeta omega n JW plus omega n square, okay? And so we can collect all the terms omega n square minus omega square plus J 2 zeta omega n W, okay? These are the terms. And so in this case we have the magnitude of the system response can be calculated with what the square roots of the what the omega n square minus omega square plus 2 zeta omega n omega, okay? And so if the frequency is increased, and then at always we increase the responses of the what these terms, okay? And also we can calculate what the GW angle, phase angle, in terms of what the arctan 2 zeta omega n omega divided by omega n square minus omega square, okay? These are the two terms for the what? For the R applications. And so how can we analyze this response based on the different frequency ranges in the what? In the Bode plots. We can write a code in here just like this one, right? And so we can copy up the whole of these things in here just like this one, but in this case S square zeta omega n form, okay? And so we can copy off the whole of these things in here and uncomment, and so we should create the zeta value in here, for example 0.5, and Wn can be considered as 2.pi.10, which means that this is the natural frequency in radian divided by seconds, and so this is the 10 value in here. And after that omega is in here, and so the magnitude can be calculated with what the SQRT for omega dot square times omega square times zeta square plus omega dot square omega n square, okay? And also we need to give the square, right? These are the what the R generation of the magnitude, okay? And so R the default magnitude is in here just like this one, and the phase of the R algorithm should be calculated with what the 2 times omega times omega n times zeta dot and omega dot 2 minus omega n. Okay, and so if we rerun this code and then we have some error in here, omega. Okay, it's the line of the 104 omega. Okay, omega and omega. Okay, and so if you rerun this code and then what we can see is that the magnitude is 700, and so the magnitude is also at the value this high enough for this one. We should analyze the up to the 10 hertz in this case. Okay, and so up to 10 hertz we have the magnification of the signal up to 4000 value at the at the 1 hertz frequency. Okay, and so at the 1 hertz to 10 we have the some diminished point, the local point in here at the magnitude at this one, but we don't have any fast shifting up to up to 1, which means that if we apply the 1 hertz sinus this system, and then we will get the 4000 value up to up to 1 hertz. Okay, this is the meaning of these signals and the determination of the form. Okay, also we can derive the another form in here just like this one. For the Bode plots of the section 4 can be rewritten as the Bode plot for GS. This is the standard system of R basis S square plus 2 zeta omega n S plus omega n square. Okay, and so if we calculate the whole of these terms in here just like this one, G J omega 1 divided by J W square plus 2 zeta omega n J W plus omega n square, and so we will have this formation 1 omega n square minus omega square plus J 2 zeta omega n omega. Okay, and so if we have the complex conjugate of this system, and so we have the omega n square minus omega square minus J 2 zeta omega n W. Okay, divided by omega n square minus omega square minus 2 zeta omega n omega square. Okay, and so for the magnitude we have the G W, and this is equals to the 1 divided by omega n square minus omega square plus 2 zeta omega n omega square. Okay, and so the phase of the G W is equals to arctan minus 2 zeta omega n omega divided by omega n square minus omega square. Okay, this is how we can calculate the R terms into the magnitude and the angle forms. Okay, and so we need to return to to this code, and then we can copy all of the whole of these things in here just like this one, and so the x3 can be given in here, right? 1 divided by these forms. Okay, and so we should write this code in a different manner in here. Okay, because we have the Wn as equals to the 2. Okay, and also minus 2 to 1 400, and these ones, and we need to defect all the terms in here. The different zeta values can be used in here. Utilize 0.1, 0.5 and 0.9. okay, and so we can observe the effect of the different chosen of the zeta values in here, just like this one. Okay, and so we can create the figures and the subplots in here. 2 1 1 and hold on, subplot 2 1 2 and hold on, and 4 zeta is equals to the zeta values can be utilized in here, just like this one. And so we can search the whole zeta value by using these codes. Okay, and so for the whole zeta values we can calculate the magnitude of the the 220 times the log 10 in here, 1 divided by SQRT form in here, and so we have dot over square form in here, just like this one, the omega square minus omega n. Okay, and also 2 zeta omega n omega. Okay, these are the decimal form. And also we need to calculate the fast form in here, and 2 and minus 2 times zeta times omega n omega and omega dot omega n square. Okay, but we need to add the 180 divided by pi value for the degrees. Okay, so the subplot is created in here, and the semi-log x can be given as the magnitude value. Okay, and so display name the sprintf, the zeta is equals to the percentage 1f and the zeta. Okay, this is the first semi-log plot, and in the second case the 2 values is updated in here with the fuzz. Okay, so at the final value we need to update the subplot 211 with the grid on, and the title magnitude of different zeta. Okay, and x label should be assigned with the frequency, but in terms of the hertz. Okay, and the y label is the magnitude dB. Okay, and the legend must be shown. And also we need to give the 212 this is the fast plot. Okay, the magnitude, and this is the fast, and this is the degrees. So if I run this code, see that what is the difference between this system? First of all, the blue line is the zeta 0.1. The yellow line is the is 0.9, which means that if we are using the higher damping ratio in here, and then our system does not increase anything, always decrease the values of this term, we can lose the energy form in here, just like this one. Like the zeta is equals to 0.5, and so we have some peak in here, but always we decrease the energy form in here, just like this one. Okay, also we can create the magnitude mag value in here. in terms of the what, these terms, okay? Magnitude mag. And so if we rerun this code and then our system at the 2 Hertz, we have the some peaks up to rate of the 0.03. Okay, we can increase the system based on these times, but always we diminish the R problem. Okay, for example, if we apply the 2 Hertz signal, sinus signal, with the amplitude of the 1, and so we will get at the 2 Hertz 0.03 for the zeta is equal to 0.1. But in the zeta is equals to 0.9, we will have the 0.003 amplitude rate on this manner. Okay, just like this one. It's the 90 minus phase shift at this moment. Okay, so this is the second order Bode plot definition on this time, and so the different damping ratio can be analyzed by using this frequency response techniques. Okay, in the next lesson we will talk about the Nyquist plot. Okay.